In this video, we're going to be talking about a specific tool that we use to get more get more meaning and get more significance out of the concept of roots. So remember that if the roots of the system um, all in the left half plane of the real imaginary axis, if all the roots are on this left half plane, then the system is stable. And so what a root locus does is it allows us to um, visualize the roots of a system. Um, so I'm going to add a picture into the video here. Okay. So we've got this picture added, and we can see that we're using just a basic second order polynomial p squared plus a equals 0. And in one column here, whoops, we've got the value of a, and then in the other two columns, we've got the values of the two roots. This is a second order polynomial, so we get two roots. And you can see that when a is negative 16, you get plus or minus 4. And then as you go down, we get plus or minus 3, plus or minus 2, plus or minus 1. At 0, you have uh, a, a root of 0 at multiplicity 2, so the roots are on top of each other. And then you start to diverge, rather than along the real axis, you diverge along the imaginary axis, which is this axis right here, the vertical axis. And so the roots start to go up and down. So the roots are at first with negative a on the real axis, moving from farther apart to closer together. They meet at the origin, and then they diverge. And you can see that happening. I wish I could draw over the picture here. You can see that happening in the plot on the right, and this plot is a root locus plot. It's a root locus, and you can see in green, hopefully it's you can see there, in green is the value of P2, and in blue is the value of P1, and as A moves along, the lines of the lines on that plot move around the axis. For a second order system, we have something like if we have a system that's mx double dot plus bx dot plus kx equals 0. I'll kind of rush through the method of assumed solutions here. We would end up with mp squared plus bp plus k equals times c e to the pt equals 0. C is not 0, e to the pt is never 0. So we're left with our characteristic equation. mp squared plus bp plus k equals 0. And using the quadratic formula, you know that p1 and p2 are negative b plus or minus the square root of b squared minus 4 times m times k over 2m. And so in this case of a second order system, we can calculate our roots for various values of b, or for various values of m, or for various values of k. And using a root locus, we can explore how the system will change if we change, say, the mass, or if we change, say, the stiffness of the system. And I'll go ahead and add another picture to demonstrate this. So for this plot, this is a root locus of P, so it explores how P changes as K changes, as the stiffness changes. And you can see for K equals 0, our roots are 0 and negative 1. And then as P increases into 0.25, 0.5, etc., first the roots move closer together along the real axis, and then the roots meet, and you have a multiplicity of negative 0.5 at a stiffness of 5. And we can conclude a few things about this. So first of all, if the roots are on the um, well, let's go back here. So if you have in a second order system uh, a root of multiplicity 2 where you have non-distinct roots, um, that means that at that value of k, or whatever you're exploring, the system is critically damped. If you have real distinct roots, so you have two roots that are not the same value, but they're both on the real axis, then it's overdamped. And if you have roots with imaginary components, and they're always going to be so some real value a plus or minus b times I, and you can see that in this case a is always 0.5. We'll look at another example where a isn't always the same, but for the same given value of k, it's the same. They'll be symmetric across the real axis. The system is under damped. So in this case, if k is greater than 0 but less than 0.25, this system is overdamped. If k is equal to 0.25, it's critically damped because at that point you have the same root of multiplicity 2. And if k is greater than 0.25, then this system is underdamped, and you'll see some oscillation. And that's what imaginary roots mean, is oscillation. If you see any imaginary component, then you're going to have some oscillations. So let's go ahead and we'll add another picture, look at another example. So in this example, instead of varying the stiffness, we're going to vary the mass, and we start to see some curvature um, when we do that. So in this one, just looking at the root locus, looking at the plot and at the table, we can see that this system happens to be critically damped when m equals 0.25. For m um, less than 0.25, this system is overdamped because looking at these values, you have two distinct real roots, and for everything greater than 0.25, it's underdamped. And the position on the root locus of a given set of roots can tell you about the system. So I'll draw another root locus here. It's mostly in the left half plane. So if you have P1 and P2, we'll remember that P1, P2 is equal to minus zeta omega n plus or minus omega d times I. So that means that this distance right here is omega d. So that's the damped natural frequency. That's the frequency that you observe. So as the imaginary component increases, that the magnitude of it increases, you're going to get higher frequencies. This distance here from the origin to one of the poles is omega n. So again, by the same idea, if the points are going up and down, or if they're increasing magnitude in the imaginary direction, omega n is also going to increase. But also, if you increase it, move those poles to the left or right, you'll affect the natural frequency, which affects zeta as well. So if we measure this theta, then zeta is actually going to be equal to the sine of theta. There's a couple other relationships that I'll add here. So omega n is equal to the square root of p1 times p2, and zeta is equal to minus p1 plus p2, that quantity is in parentheses, over 2 omega n. And so you can see, if we come back up here, we see this big loopy, oh, now I can draw. We see this big loopy sort of shape that's going on. And so as we're in this region here, I'll go ahead and change my color. In this region here, we know this is related to higher values of the mass. We have a relatively low angle, and so that's going to affect the damping ratio. But as we're moving out, that increases omega n, and then omega d is also increasing, but then omega d starts to decrease here until eventually you're critically damped. And so we'll get a lot more practice interpreting these root locus plots and understanding more about physical systems just based on being able to look at this picture. We'll go ahead and finish that video right there, and that'll be it.